Hello, youth. Probability unit, theoretical and experimental probability. So you are going to have to know the difference between theoretical and experimental and then make some decisions based on what you know. Here we go. So vocabulary, very important that you understand the difference between theoretical probability and experimental. So what is the difference? Well, theoretical probability, think. Theoretical probability is what you think should happen. So this is whether you do an experiment or not, whether you are talking in theory, okay? In theory, what should happen. That doesn't mean that you actually have to follow through with an event, but this is what we think will happen. This is really just like the probability without an event happening. So the probability of what you think will happen. What you think will or should. And that's kind of a vague description, but that's kind of what it is. Just what you think, or in theory, what should happen. Experimental probability is after you've conducted an experiment or done the event, this is what actually happened. So the actual results of an experiment. And then you can compare the two. So if I theoretically should get a heads half of the time when I flip a coin, and I flip that coin 50 times, and I get heads 26 of the 50 times, that is relatively close, my theoretical and experimental. So theoretically is what you think or what should happen in theory of what should happen based on my odds. Experimental probability is what actually happens after you've completed an event. So if you wanted to flip a coin 10 times, theoretically, how many times should it land on heads? So something you have to think about is make sure you're reading what the question's asking. So it's not asking me for the probability here. It does say theoretically, so how many times do I think, but it's not saying the probability of it happening. It's saying how many times. So there's going to be a difference in the number of times, which is going to be a whole number, or when it asks probability, then we have to remember probability is a number between 0 and 1. So this question can be tricky because naturally I want to say 1/2, right? Because that's the probability of getting a heads. But here it is how many times. So I think theoretically the probability of getting a heads on a coin is one of the two choices. So then I think, okay, if I do it 10 times, and again, it's just theoretically, it's not actually happening, I can see that that should be 5 times. So my answer should be theoretically, I should, not would, get a heads 5 times. So again, my answer can be a whole number when it's asking for the number of times. Whereas on the bottom here, it says if the coin landed on heads 7 times. So they're saying this actually happened. So the experiment was conducted. What is the experimental probability of the coin landing on heads? So from the experiment, the probability of getting a heads, then out of the total possible, it happened 10 times, and we got heads 7. So that'd be 7 out of the 10, or 70%. So we're just going to try a couple here. And, if you want to look at them, pause, see if you can do it on your own. Great. If you want to see what I'm doing first, that's also great. A dice is rolled 24 times. So this is my sample space. This is what happened. Okay. Theoretically, maybe before it even happens, before you know the results, theoretically, looks like that's spelled wrong. We're missing some letters there. No, theoretically. Theoretical probability of rolling a 5. So I think of a dice. I could have 6 outcomes. A 5, probability of getting a 5. 5 is one of the 6. So theoretically, it should be a 1 in 6 chance. If it were theoretically then 1 in 6, you could say I would get 1/6 of 24, right? Times 4 there. So that should be 4 24ths. We'd think that I'm going to get it 4 times because the probability is 1/6. Experimentally, if it actually happens, this is where you have to be careful because a lot of numbers show up It says if a 5, so that's what they're talking about, was rolled, and this is the number of times it was rolled. If a 5 is rolled 8 times, what is the experimental probability? So what actually happened? That means it was rolled, a 5 actually was rolled 8 out of the 24 times. Those share a factor of 8. So experimentally, what actually happened was a 5 was rolled 1/3 of the time, which is different than what I expected in my theoretical. In the above experiment, what is the experimental probability of not rolling a 5? So again, this is what actually happened, not what I think is going to happen. So if we rolled probability of getting a 5 was 8 out of the 24 times, the complement to that, not 5, would be the remaining out of the 24. So, right, what is the remaining part? You think, right, 18. How many more of those? So 16 of the 24 is not, which is the same as 2/3. Okay, so if a spinner, this spinner on the right, is spun 40 times, so that's like if you do an experiment, that's how many times you're spinning it. But then it asks, what's the theoretical probability of landing on a 2? So again, the experiment, how many times doesn't necessarily matter right now. On the spinner, we need to think, well, I see that we're looking for the probability of getting a 2. There are 4 total outcomes. One of those sections is a 2. So theoretically, I should get a 2, 1 out of the 4 times. If we consider the number of times, theoretically, out of 40 then, that should be 10 because those are equivalent. So we should get a 2, 1/4 of the time, theoretically. If we do the experiment and we got a 2, 16 times, what is the experimental probability? So what actually happened for getting a 2? The actual result of out of 40, we got a 2 16 of those times. And that simplifies. They share a factor of 4. And they also share a factor, so let's see, they share a factor of 8 also. So that's 2/5. Okay, so we went from, theoretically, it should have been 25% getting a 2. And we actually got it 40% of the time. What we thought should happen, what actually happened. Experimental versus theoretical. So here we have a graph, spinner results, that show they have 3 equal sections, and it was spun 60 times in an experiment. So that actually happened. So we want to know what is the actual results, the actual probability of spinning a red. So we see that red was 24 outcomes. Well, to figure out what the total is just 30? No, we'd have to add up all the total outcomes. So we would add 21 and 24 is 45 plus 15, so that's a total of 60. So it actually happened 24 out of the 60 times. We can divide those both by 4 to start. Oh, we can divide them both by 60, or 6, I mean. They share a factor of 6 for 4/10. Oh, they share another factor. Oh, they shared 12. I could have done that. Divided by 2, 2/5. So red happened 40% of the time. So now it says compare the experimental probability found to the theoretical. So we already found that the experimental probability of red was 2/5. Theoretically, if there were 3 equal spinners, like it said, equal sections, red should happen 1/3 of the time. So what we could say is the experimental probability happened slightly more frequently than what we would have expected in our theoretical of 1/3. So 40%, it happened slightly more than we would expect. So you can use probability to help you make predictions about future events And obviously not an exact science, but again, it's prediction, it's probability, it's not always certain. So here we have data from a video streaming services about customers and their selections. So from the chart here, we can see the type of genre that people are watching and then the number of customers selecting it. So you are asked a question of what is the probability that a customer streamed comedy? So what you can do then, again, theoretical probability here, well, not theoretical, actual data, sorry. Probability of someone selecting comedy, you can see is 580 was the favorable. Well, to find the total, you're going to add them all up. When I add all of these up, I get 2,000. So that means that 580 of the 2,000 customers selected comedy. And of course, I can reduce that fraction. I see they both end in a 0, which means they can be divided by 10. So then I have 58 out of 200. They're both even, so I can divide them both by 2. So 29 for every, out of 100 customers, 29 of the 100 select comedy. So knowing that is just one way to show the probability that someone will pick, 129 people. And then here, we can use that data to make predictions also. So suppose the analyst expects 5,000 customers this year. What's the likelihood that someone's going to pick drama as their selection? So what I see here about drama right now is that the drama selection is currently 450 out of that 2,000. So you have a couple options. You could change this to a percent and multiply that percent by the total, right? Because we want the percent of all of them. It should be equivalent percent, or you can use your proportion. So I might simplify this first, and again, I see that they both end in 0. So then I have 45 out of 200, and that, if I wanted to know the percent, that is the same as 22.5 out of 100 if I wanted to know, so that'd be 22.5%. Otherwise, I can just say, okay, so 450 out of the 2,000, or 45 out of 200, that should be the same as how many customers selecting it out of 5,000. If you remember from your proportion learnings, you can use cross products to solve. Similar here if you did it this way. If you did the percent, you're really doing the same thing. If you notice, it's how much out of 5,000. Same deal from our percent unit. So I can do my cross products, and I get, oh geez, what am I doing here? 225,000 is the same as 200 times what? So then you divide to solve for your variable. So some prior knowledge coming together here. And we find out 1,125 is our answer. So that represents that we could expect, based on our probability and our understanding, that 1,125 people of those customers would select drama. So you have a lot of old prior knowledge. It's up to you on how you connect numbers and what you want to use there. So just a quick little recap before the ones that I want you to submit. Theoretical probability is what should happen. Without doing an experiment, what do we think should happen before anything happens? And then experimental, what actually happens? What should happen? What actually happens? Think, do. The higher the number of experiments, the closer the theoretical and experimental probability will likely be. Right? If I roll a dice once and I don't get the number I'm looking for, well, that makes sense because I had 1 in 6 chance. If I roll my dice 100 times, it's more likely that those numbers will align. So this is really important to understand. The more often you do an experiment, the closer the results should be. So this is where I want you to pause and I want you to try these and submit them, and then I'll post the answer key later on so that you know that you did them correctly. But make sure you read. It tells you how many times. Theoretically, remember, theoretically happens. The experiment really doesn't matter until it asks you about what happened in the actual experiment. So theoretically, what you think should happen, experimental probability, what actually happened. So be careful there. Same thing for number 2. Just make sure you read and use your clues, and I can't wait to see your work and see what you're thinking. Have work, not just answers. Don't forget to upload your notes, and have an awesome day.